Hi, I'm Peter Lane. I'm a geologist. I live in the southwest of WA, and this is a bit about the geology of the Cape to Capes region and the soils we find down there. The Earth is considered a rocky planet, but actually it's basically liquid with a very thin crust and a very thin area where life exists, a biosphere with life in the atmosphere, on Earth and in the oceans, and deep below the Earth, but it's only 20 kilometres thick. So it's a very delicate part of the Earth, is the biosphere. It's a very active planet with a crust that's constantly moving, and these are the elements of the crust. You can see there's oceanic crust that might split and open. There's continental crust, and they move too, and that's formed the Earth and is particularly relevant to our part of the world. Slide 4. This gives an indication of how thin the crust is. It's somewhat like an eggshell. This is a giant split down the middle of the Atlantic Ocean. The Atlantic Ocean wasn't there 200 million years ago, and you can see that the continents of South America and America have moved away from Africa and Europe, leaving a giant crack down the middle. And this crack goes all the way up to Iceland, where you can walk down it with basically America on one side and Europe on the other. Slide 6. These are the elements of crust that are particularly of particular interest to the southwest here. On the right-hand side, there's a collision of crustal plates, of continental plates, and in the middle here we see a continental plate shedding sediments into a sedimentary basin. They are the aspects we will be talking about. But looking at Western Australia on slide 7, I've divided it into two major geological provinces. The big one, the red one, is the ancient province, formed up to nearly 4 billion years ago, and it contains some more recent sediments, but not many. And to the northwest and to the west is where that old continent has been eroded, and the sediments dumped into very large sedimentary basins. In general terms, minerals are found in the ancient part, oil and gas are found in the modern sedimentary basins. And this can be seen on slide 8, where up to 250 million years ago, the ancient part of Western Australia, the old rocks, were quite mountainous, and they had been eroded and dumped into these sedimentary basins to the west and to the northwest. And in Western Australia we have a range of these geological provinces, quite extraordinary really for any state in Australia or anywhere in the world to have such a range. We have 3 cratons, which are the very old and very stable areas, 5 orogenic zones where there have been collisions of crustal plates, and 7 large sedimentary basins and many smaller sedimentary basins. Slide 10. On the left we see the main geological provinces in Western Australia, and to the right we see a satellite image, and probably the most prominent thing in there on that satellite image is that whereas we'd like to see some definition of the geological provinces, and indeed we can, but the main element we see is this line in the southwest, and that's the edge of the wheat belt. This is the massive clearing of the wheat belt that occurred during the 60s and 70s. Slide 11 shows the old Yilgarn Craton, the oldest part of Western Australia. And to the left is a collision zone. It's called the Pinjarra origin, and that's very important to the geology and the landforms in the southwest. Slide 12 shows the formation of that origin. It was formed during the assembly of Gondwana about 500 million years ago, where Greater India and Australia collided, and also that incorporated Antarctica and East Africa. Slide 13, eventually Gondwana began to break up. So it wasn't long after the India and Australia collided that actually India then began twisting off and moving up to the north, although this took a long while. And this opened up a sedimentary basin called the Perth Basin, which can be seen on slide 14. As India moved off, it opened up the Perth Basin, and old sediments of the Perth Basin began to be deposited there about 480 million years ago. India broke away from the Darling Fault, which on slide 15 you can see as a surface expression as the Darling Scarp. This is taken from the Darling Scarp looking over to the city of Perth. Slide 16. As India moved away, it left behind a bit of that continental mass, which now forms the Leuven Naturalist Ridge. And this is where Margaret River is, in the middle of that ridge. And the sediments began to pile up within the Perth Basin from rocks eroded from the Yilgarn Craton. After India had departed, we were left with the sediments being accumulated in the basin. It never got very deep in the southern part in what's called the Bunbury Trough, and we don't have any marine sediments there. They're only sediments, rivers, lakes, that sort of sedimentary deposit, continental deposits. And this lump of India that was left behind was an island within that sedimentary basin. 18. This just gives a better location, a more detailed location of the Bunbury Trough, with Nannup, the little red dot on the right, and to the west, Margaret River is, as you can see, is located on the Leuven Naturalist Ridge on the old bit of India that fortunately wasn't dragged away with it. I've included this slide just to show the roads for people who might want to identify where they might sit, what sediments are under them. And this has a strong bearing on the soil types within the area. I've drawn a cross-section across that area just to show how different the rock types are. And this shows the piece of India that was left behind. It's mostly granite and gneiss. They are igneous rocks and metamorphic rocks. And also the further to the east rather, beyond Nannup, are similar rock types of the Yilgarn Craton. But in between are sedimentary rocks of the Bunbury Trough, that southern extension of the Perth Basin. And this is very important for water. Water comes in from rainfall. It's held within these aquifers, the Laterite Aquifer and the Aragidee Aquifer. It's expelled, it's discharged into the Indian Ocean and the Southern Ocean. These aquifers, the Aragidee Aquifer for instance, is about 145 million years old and even older. And yet the the oldest water found within the Aragidie is about 40,000 years. So you can see it's a very active water system. Water is consistently flowing into it and flowing out of it. And the important part about the shallow aquifer and the Aragidie, where it becomes shallower, is that it supports what's called groundwater dependent ecosystems. So groundwater dependent ecosystems sounds rather esoteric, but there are many of them. Slide 22 shows the extent of groundwater dependent ecosystems. All the streams within that Bunbury Trough area are dependent on groundwater support, and the coastal plains, the Swan Coastal plain to the north, the Scott Coastal Plain to the south, are dependent on groundwater support. And in fact, if that groundwater was taken out from those areas, for instance by using groundwater faster than it's replenished, then those soils are prone to soil acidification, the formation of acid sulfate soils, which are very environmentally hugely damaging and damage human structures too. For instance, cement and acidic soils do not get on very well. Slide 23, this is a groundwater dependent ecosystem, one of many along Margaret River. This is Canebrake Pool, photo taken in April of 2009 following a very dry summer. You can see the pool has not declined, has not dropped at all, and this photo is actually taken from the bed of the river. So no water coming into the river, totally dependent on groundwater support. This is a photo of a lamprey in Milyanyap Creek, which is a tributary of the Blackwood River, and it's not the lamprey that's so interesting, it's the very clear water. This again is taken in summer. Clear, cool water is discharged from the Aragidie formation, and that's what keeps this this ecosystem alive. And slide 25, discharge of cold, clean water from the aquifers is critical to the health of the river system and to the Hardy Inlet, which lies behind Augusta. On the Lunar Naturalist Ridge, which is granite and gneiss, this is where groundwater is not available. There's what's called superficial aquifers, which are very shallow and essentially part of the soil profile. Farmers don't get their well from bores on the ridge; they get their water from dams. On the western side of the ridge, there's limestone. This limestone was deposited as sandhills originally, and mainly during the glacial ages of the Northern Hemisphere. During these stages, sea levels were up to 120 metres lower than they are now. The seabed was exposed. The seabed contained a lot of shell material, a lot of coral material, and this was blown ashore, and it's still happening today. In fact, that sand is blown ashore, heaped up into sandhills, and through percolating water this is dissolved and redeposited as limestone. So there is subsurface available in limestone in what's called karst topography, essentially caves or porosity within the limestone, but this is pretty ephemeral. It depends, in most places at least, on recharge during the winter, and it's drawn out during the summer. They are not reliable wells, not reliable groundwater. 27. This shows the different soil types across those regions. Of course, to the west where the limestone is, it's very high pH soil, lime soil, and often very sandy. On the ridge we have more interesting soil types. As the granite weathers, we get a range of soil types. We'll look at those a bit closer later on. And to the east, within the trough, we get very light sandy soils. On the coast to the west, there's lime sand, generally over limestone, or maybe directly on granite, and then on granite. So a very high pH soil. On the ridge, the granites and the nice weather and the aluminium silicates, which are the main component of these rocks, weather into clays. Clay is very water retentive, and the quartz that's present weathers into sand, and sand is very well drained. Sand soils drain very quickly. So these are very good soils for growing, for instance, vines, where you have a well-drained surface and yet a water retentive deeper layer, so vines can survive over the dry summers. Laterite is often formed on these soils, and that adds to the well-drained upper soil characteristic of them. Inland you still may have a laterite formed, not always, but over this area to the east of the ridge the soils are sandy, very little mineral component other than quartz, very light, and growing there is not much more than hydroponics. These are soil profiles taken on our place. Both you can see sandy soils about the top metre, and beneath that we go into clay. In the Bunbury Trough, here's the soil profile, considerably more than a metre, and it's sand all the way down, and that will continue until you get onto sandstone, so very little variation.